All right. Hi, everyone. My name is Samantha Suero, and today I'm going to be talking to you about electric generation and distribution. So, what we're going to be learning in this presentation is why demand and consumption set energy prices for commercial buildings, why transformers reduce AC distribution costs, and why most electrical installations are grounded. Now, if you don't understand some of this stuff, that's no problem. Hopefully, by the end of this presentation, you'll be able to get a good idea of what all this means. So to start with, we're going to cover the basics: power, work, and energy. Power is the rate at which work is done. The units for that are kilowatts, and horsepower. To find work, you're going to be multiplying power by time, or you can find it by multiplying force by distance. And the units for this are kilowatt hours or horsepower hours. And then there's energy, which is the ability to do work. And it can be compared to work, but it is not the same. Work is going to be when you're exerting energy versus energy is something that can be stored, like potential energy. You can have potential energy stored in a spring, versus work, it's not really anything that can be stored. It's more of the action of energy. And the units for energy are joules, and it can also be used to describe the heat content of fuels. So next up is demand and consumption. So how do utilities charge for electricity? They meter two different things: power demand and energy consumption. Power demand is going to be the largest kilowatt load during any 15-minute time period, and energy consumption is going to be the consumption in kilowatt hours based off different rate schedules. And rate schedules are going to be at different prices that the company will be charging. It's not a certain set thing. They have to do it off of these schedules. So commercial buildings or places, those are going to actually do both power demand and energy consumption. So when they charge them for both of those, usually power demand will be the higher part of the bill, because when you look at a commercial building like a church, it's going to have a high energy usage in a very short amount of time. So then, of course, power demand looks larger because it's based off that time period. To reduce these costs, you can use control systems that are going to limit your demand, and it just kind of limits how much power you can use and sequences it over longer amounts of time. So residential is only metered for energy consumption. They do not take into account power demand when pricing your electricity usage. And that's going to be based off those utility rate schedules. So if you ever want to calculate it, make sure you know the utility rate schedule. Otherwise, whatever number you get, it's not going to be what you should be charged. So there's going to be two types of current: direct and alternating. So a direct current is electron flow generated by batteries. This means chemical energy is being transformed into electrical energy. And this is going to be going in a single direction from a negative to a positive terminal. This is going to be used in emergency lighting, in your computer, in your phones, anything with a battery, really. And then alternating current is electron flow generated by generators. And that sounds dumb, but that quite literally means mechanical energy is being transformed into electrical energy. You need something generating electricity. There's no chemical reaction going on. And this is going to create electron flow that will actually reverse direction at regular intervals. So unlike the DC current, it doesn't go in one direction. It swings back and forth. And then the uses for this are electric utilities, appliances, motors, air conditioners. And by appliances, I mean something that has to be connected into the wall to work, like your coffee machine or I don't know, either way, like a coffee machine or a vacuum, something like that. So why do the utilities use the AC current? The AC current is used because it is of a higher voltage, and this higher voltage means that you basically are going to have a reduced current. So when they're going over those power lines, a reduced current means less loss, as it goes from one place to another, which is good. You don't want to lose as much energy. So next we're going to talk about what sources generate our electricity. And according to the textbook, the utilities use falling water or burning fuel to turn generators, renewables or non-renewables, and 10% are hydroelectric, 90% non-renewable like fossil fuels or nuclear fission. But more recent data, if you check the EIA website or the U.S. Energy Information Admin, in 2022, we used around 4.24 trillion kilowatt hours of energy, and 60% of that was from fossil fuels, 18% from nuclear, and 22% from renewables. If you're interested more on the specifics of where that all comes from, go check out the website. I did link it below. and it's in my sources. So next is generating efficiency. Now, there's never of course, whatever you have goes in, comes out, but according to the second law of thermodynamics, there's always going to be heat loss. And so that greatly affects our electrical production. So a typical electric utility, whenever they convert 10 units of fuel, you're only getting 3.5 units of that as electrical energy, and the other 6.5 units are going to be waste heat. And obviously that's a lot of waste. So, and this question says, which is more efficient, nuclear plants or fossil plants? And nuclear plants are going to be more efficient, or I'm sorry, nuclear plants are less efficient because they use reduced heat to create their steam, and I guess more heat is lost, or there's more waste heat in that entire process than the quick flash burn of fossil fuels. Although neither one's good for the environment, but so going on, how can we use this waste heat? There's two ways. There's cogeneration, which is when the power producer will sell that surplus heat to other places, and then there's total energy, which is when a site that is an on-site generating plant will use that waste heat back onto their plant. So they'll use it for the building's heating, for refrigeration, for anything of that sort, just to use that heat in another way so that it's not lost, and you can save costs in other ways. So now we're going to talk about AC generators. So first off, a term to know is voltage, which is generated when magnetic flux moves through a conductor, and if that is connected to a circuit, then current will flow through that circuit, because you can't have current unless it's a full connected circuit. So in North America, the standard is going to be 60 hertz alternating current, or it's also called 60 cycle. And the rotation of generator, what that means is that the generator is rotating 60 times per second, and that will cause an alternating current 100 times every second. And now this is different for other places in Europe. I believe the standard is, don't quote me on this. I know it's a lot lower. I think it's 40. And then in aviation, it's a much larger number, but it all depends where you're at. And I believe it's lower in Europe because air conditioning isn't quite as standard as the US. But moving on, we're now going to talk about single-phase power and three-phase power. So whenever you have these alternating currents going through the lines, you're going to have two different types. The first is single-phase. This is when you have two wires and the flow of electricity goes through a single conductor, that first wire that we're going to call the load wire, and then it is returned through another wire, which is going to be the neutral wire, because we need a full circuit. This is normally used for residential applications, and the reason for that is because it's a lower voltage than the one we're going to talk about next. And utilities, the way they do this is they'll usually designate phases to neighborhoods, and by designating phases, they reduce the number of distribution lines they need. So let me go into this. So if they designate so they have three phases, A, B, and C. They'll designate neighborhood 1, and it's going to be A to B. Neighborhood 2, it'll be B to C. And then they need to connect it all back together to form that circuit, C to A. That way they can have less lines because they don't need another returning line, so to say, and it all forms a circuit together. To solve an equation, to solve for either the current or the watts or the voltage, we're going to be using the equation E times I equals W, which stands for voltage times current will give you watts. And I pulled an example problem from the book that you can look at. I'd go into it, but I got to keep a time limit. Next is three-phase power. That's going to be 4 wires. Electricity flows through the same thing, but there's now 3 separate conductor wires, and they're 120 degrees apart, which is important. We'll get back to that. And a single return neutral wire. This is more of a commercial use. It is much higher voltage, and they need to make sure that the loads are balanced between these wires. And that's also very important because it means less losses and more efficient use. And this is going to be carrying your motor loads, so if you have heavy equipment, or in this case, any motor that is greater than 5 horsepower, you're going to need 3-phase power connection. Or if you have a motor that's greater than half the horsepower, which I'll be honest, I can't quite understand. You can ask Dr. Salih to explain that. And that needs to also be a 3-phase power connection. So the equation for 3-phase power is a little different. It's E times I times square root of 3 equals W. Now, square root of 3 actually comes from that 120 degrees we talked about earlier, because the sine of 120 degrees will be square root of 3, and that's why we have it there in the equation. Now we're going to talk about transformers. Transformers are those little like box circle thing, like cylinders that you see up connected to the power lines. And a transformer is an iron core that's surrounded by two circuit loops, and these are called windings. There's a primary winding, and it's connected to the power supply circuit, and then there's a secondary winding, which is connected to the building service circuit. So basically what these transformers do is they transform the like really high voltage that's going through these wires, the primary winding, to a lower voltage that we can actually use for normal building things, because like if it's a crazy voltage, we can't really use that. And that's what they do. So they trade the AC voltage for current. So yeah, the voltage to current, and they lower it. The capacity of these are going to be rated in kVA, or kVA. And for the residential side, it's going to be transforming it into 240 volts. For the commercial, it's going to be transforming it into 480 volts. And then another example is like at an industrial plant, they'd be a transformer converting it to 13,200 volts. Pretty high. Now, why is a high voltage preferable? Like, why don't we just make the lines not carry so much voltage in the first place that we have to transform it? The reason for that, as I believe I actually mentioned it earlier, is that a higher voltage means you're going to have less energy losses across the line. And of course, you don't want to waste energy. So it's just more preferable because you'll lose less energy. It's more efficient. Now we're going to talk about the power factor. And this might be our last slide, or we have one more. So first off, there's inductance. And inductance is the tendency to oppose changes in the circuit's current. And windings have this property, like the thing we talked about earlier. And then there's inductive reactance, which is like, it further goes on into inductance. It's saying that this tendency to oppose changes results in a delayed current flow, meaning that the current flow is going to peak after the voltage peaks. It's lagging behind. So lagging current means a lower kWh and less income for utilities. So what power factor actually, like the definition of it, is a number index used to quantify this lagging current. So a building that has no motors or coils would have a power factor of 1. Like there's not any lag going on. And then a building with substantial motor loads is going to have any power factor less than 1. So the equation you're going to use for finding the real power is, it's once again different between single and three-phase. You're going to be multiplying amps times volts times your power factor, and that's going to equal watts. And the same for three-phase, except you have to factor in that square root of 3 for the 120 degree space between them. So a building with a lower power factor is actually required by utility companies to use a capacitor, or they get a surcharge. And the reason for that is we're going to go to our question. Is a higher or lower power factor a more efficient use of energy? And the higher the power factor is, or the closer it is to 1, is the more efficient use of energy, which is why utility companies are going to be surcharging you if you have a lower power factor. And so what does a capacitor do? Like, how does that involve? A capacitor actually makes it more efficient because it gives you high peaks of voltage, which gives you that lower current, which is good. And then last thing we're going to talk about is grounding. Grounding is basically, it means you've connected your circuit to the earth. Grounding dissipates false current, so if like it gets hit by lightning or something and like a super high voltage goes into the circuit, grounding should dissipate it so that it doesn't shut everything down. And connection can be made to underground piping or to a copper-coated steel rod that is driven into the earth. And this saves utilities money, and the way that this it saves them money is instead of having to make like a full circuit, the earth actually acts as a circuit. So as long as they connect it through that end thing, they don't need that extra wire, and that saves them money. And that's it for today. This is just my page of sources. Most of this came from the textbook that we have for the class, but I also, below it is the EIA website. Then there's just the definition for thermodynamics, and that last one's about connections, single and three-phase. So that's it, and thank you for listening to my presentation.